Okay, so this is lecture number 2, part 1. And this sequence of lectures, the lecture 2 series that is, will correspond to more or less chapter 2 of your textbook. So, lecture 2, part 1 is the title. And we're going to start off with our chapter 2 or lecture 2 discussions with a little bit of geometry, and we're going to talk about tangents, or in particular tangent lines. All right, so what is a tangent line? What is a tangent line? So typically, from grade school, we recollect that a tangent line is something that is a line that touches a circle at one point. So let me see if I can draw a picture of such. One second, let me pull up my graphical editor. So here you see a drawing of a circle, and was somewhat faint. Let me highlight it, accentuate it with red here. You'll see this line right here, which I think is denoted as T, and you'll note that this line touches this circle at exactly one point. So we say that this particular red line is tangent to the circle at a particular point. Well, suppose we have an object that's not a circle. We can still devise what tangent lines are to other kinds of geometric shapes. So for instance, let me see here, let me pull up another object. Select print screen. So consider a hypothetical function that I've drawn. So consider it as shown in black here, and again, we have a tangent line to this function, and I'm not defining the function yet, at point P. Now note that this tangent line, the blue tangent line, intersects the function at 2 points, at least 2 points. But for clarity's sake, we say that the blue line is tangent at point P, insofar as if we pick a neighborhood, which I've delineated by these open parentheses, if we bracket P, point P right here, within a neighborhood which is delineated by P, which is basically a range of X values, and the line, the blue line, touches the curve, the function at only one point in this neighborhood, then we say that the point of tangency P is P, and that the blue line is a tangent line. All right, so we can ask more general questions. So for instance, how about we have something like this? Find an equation of the tangent line to the parabola y is equal to x squared at the point 1, 1. Right? So let's analyze what this is asking for. So the question is, we want to find the equation of the tangent. Let me change that. Of the tangent line to the parabola y equals x squared at p1, 1. So what are we asking for? We're asking for the equation of a line, a particular type of line. All right. So that would look something like this. So here I've got a sketch in the xy plane of y equals x squared. Right here. Here's the formula. So y equals x squared, vertex at the origin. And the objective, or the question, is asking for what is the equation of this green line? Okay, which is denoted as t. All right, so the letter t represents the line, the set of points that comprise this tangent line. And we want the equation of that green line. All right, so what can we deal with here? Well, we can use point slope form for the equation of a line. All right, so how about we do that? So recall that the point slope form, in the general sense, of the equation of a straight line is simply this. Okay, so there's the answer. Well, it's not quite the answer. We need values for x1, y1, and m to complete the answer to the question. So we already have x1 and y1. It's right here in the definition of the point. So we can plug those numbers in. So we have y minus 1, because y sub 1 is equal to 1, is equal to m times x minus x1, which is 1. So let me plug in 1 for x1. Okay, so that is, we're getting closer to the equation of the green line. So what's missing? Well, obviously, we need a value for m. So what is m? Okay, we need to compute the value of m. Well, in the case of the green line, we have the coordinates of only one point. And if you recall, the slope of a line is determined by the coordinates of 2 points. Okay, so in particular, if we have 2 points, the slope of a line is determined by the difference of the ordinates divided by the difference of the corresponding abscissas. Okay. Now, in the case of the tangent line, we only know x1, y1. We do not know x2, y2. So we have a bit of a dilemma here, don't we? Well, so the way we compute m is we kind of have to resort to some approximation techniques to compute the m, because as you can see, m is what? Basically that, right? Rise over run. You may recall from elementary school or grade school. So if we consider this blue line, which is determined by the points P and Q. Okay. Now this blue line has a particular nomenclature. It's called a secant line. Secant line. All right, so this is a secant. A secant line is a line that connects 2 points on the graph y equals x squared. All right, so, or for any function. If you choose 2 points, 2 distinct points on the function, on the graph of a function, and you connect those 2 distinct points, then the connection, the line segment or the line connecting those 2 points is henceforth referred to as a secant line. So like, for instance, you may have recall from geometry from the distant past, if I select 2 points on the circle, okay, and I connect the 2 points, well, that line is called a secant line, okay? And the same follows with this case of the parabola. So, well, if we resort to using the secant line, then we can kind of formulate an equation for the slope of the secant line, okay? So we can do that. So let's postpone, at least for the time being, trying to construct the equation of the tangent line, and let's construct the equation of the secant line. And then once we construct the equation of the secant line, maybe we can do some manipulations of the secant line's equation to transform it into the equation of a tangent line. That may be something we can try. So, let's say, for instance, we can calculate the slope of the secant line, MPQ. So when I use these subscripts PQ, that means a secant line. When I write M without subscripts, that typically denotes a tangent line, unless otherwise stated. Okay, so we have the coordinates of P given as 1, 1, right? Now Q is an arbitrary point on the parabola. So point Q, okay, its abscissa, let's just say X, any number X, okay, except for 1. And if X is the abscissa, then the ordinate must be X squared, right? Because Y is equal to X squared. So we have a generalized coordinate for Q. And with that, we can calculate the slope of the secant line, or at least a function of the secant line, of the slope, for the slope of the secant line. We can calculate a function for the slope of the secant line. So that would be basically the ordinate of Q minus the ordinate of P divided by the abscissa of Q minus the abscissa of P. And go ahead and plug in the values. So the ordinate of Q is X squared. Okay, and the ordinate of P, of course, is 1. The abscissa of Q is X, and the abscissa of P is 1. So there we have a slope, or at least a function for the slope of the secant line. Okay, now look very carefully. Now, let's make one assumption here. Let's assume X is greater than 1 for the time being, right? So if X is greater than 1, then you'll see that Q will occur on the branch of the parabola to the right of P for all intents and purposes. So if we assume X is greater than 1, what would happen if, right, so let me draw a little perpendicular here. Here's QX, right? And let me draw another perpendicular right here. And this is P of X. All right, so what would happen if we manipulated the abscissa of Q such that we made it smaller and smaller until the abscissa of Q was almost the same as the abscissa of P, but not quite? What would happen? How does that affect the appearance of the secant line with relation to the tangent line? Let me see if I can show you another example of what this kind of dynamic would produce. Pull up a graph here. Let's see here if I have it. I'll check to see if I have it. Bear with me. I'll pull it up on a browser here. One second. I'm looking for an example. Let me go to another page, insert another page. And let's see, let's insert a browser. Show you something, a trick here. Okay, so look at this graph. This graph, the graph drawn in blue is the equation f of x is equal to sine x plus 0.3x. So don't worry about how to plot it just yet. We'll get to that later. And look at the red line. See the red line? Well, the red line connects 2 points on the graph f of x. Okay, so let's say for the moment here, we'll label this point Q. Okay, and oops, let me write it again. So there's Q and there's P. Okay, so 2 distinct points on the blue graph. Now, what would happen? Well, we can do, before I ask the question, see, okay, so they're the 2 points, and I'm just adjusting the coordinates of the points. Okay, and you can see the coordinates of the points. Now, what would happen? Okay, so let me bring it back. So there's Q and P right there. What would happen if from the previous question, if I drove the abscissa of Q toward the abscissa of P? In other words, I made the x part of the coordinate of Q approach the x part of the coordinate of P. Well, something very interesting happens. Watch what happens to the red line. Now again, Q, the abscissa of Q is walking along the blue graph toward the abscissa of P. Okay. See the 2 points Q and P are getting closer and closer together until they merge into 1 point. So let's make it merge to 1 point. Right? So if I make it exactly 0, what do you think happens? Okay. All right. Okay. When the 2 points Q and P are on top of each other, all right, we see only one line, and that red secant line became a tangent line. Okay, so that's one of the things we need to do. So we can show that. So we're going to do the same thing with this parabola. So in other words, as Q of x approaches P of x, the theory goes, or the thought goes, that we anticipate that the slope of the secant line approaches the slope of the tangent line. And once that happens, then we have the slope of the tangent line, and we can finally extract out the equation of our tangent line. Okay, so let me show you in the case of the parabola. Let me do a screenshot here. Okay, go to the next page. Okay, let me get rid of this particular example, and let's put back in the our parabolic example. So now here we have a couple of structures shown. The black curve is our parabola, and the red curve now is my secant line, defined by the points Q and P, which reside on the parabola. Okay, so there's my initial cut. And let's say the blue line would be my tangent line, which intersects the parabola at only point P, and is labeled T. So in the second frame, note that Q has moved closer to P. And look at the, I guess in a sense, the geometric distance between the secant line and the tangent line. Okay, it appears that the secant line is moving closer to the tangent line. In other words, it seems to be lining up, matching up with the tangent line as Q moves closer in. Okay, and then finally, in the last frame, you'll see that Q has moved even more closer to P, and the secant line defined by QP is almost on top of the tangent line. Okay, so what's going on here? Well, in calculus, we can write this as a limit problem. Okay, we can write it something like this. We can say that the limit, oops, it's not a nice letter there, it's hard to read. We can say that we have what's called a limiting problem. The limit as point Q approaches point P of the slope of the secant line is equal to the slope of the tangent line. Okay, at least when the abscissa of Q is greater than the abscissa of P, which is 1. Okay, so now we can substitute in equations for this, and we can say that the limit as x approaches 1, and we know the formula for MPQ from the previous slide. It was defined as x squared minus 1 divided by x minus 1. All right, because the way we move Q is we make adjustments in the abscissa. Okay, we make adjustments in the independent variable x. All right, so now another thing about this limit is that x approaches 1, but x can't be 1 for obvious reasons, right? We can't put the exact value of x equals 1 here because we would be dividing by 0. So the limit operator says we can take on all values of x except for 1. Okay, so what this means is we can get pretty darn close to 1 as long as we're just a little bit smidgen off of 1. And so that opens up to building a function table. All right, so let's do that. And here's what happens when we build a function table. Something very interesting happens. Let me see if I can just go ahead and insert a table. Insert a smart notebook table here. 1, 2, 3, 4, 5. 5. We'll make it 5 rows. I'll go ahead and add 6, and then say 2 columns. All right, so I'll put, say, x here, and then we'll calculate MPQ here. For x values close to 1, but ever so slightly greater than 1. So let's say we start off with x equals 2, and if we do that, and if we plug in 2 into this equation right here, we'll get that the slope of the secant line is 3. Right? So now, again, our objective is to approach 1, but not be at 1. So that means to get to 1, we have to go less than 2. So the next value of x, say we plug in 1.5, and then we'll observe that the slope of the secant line is 2.5. And so we can get a little bit closer, right? So if x is 1.1, then my calculator shows that the slope of the secant line is 2.1. And we can still get closer, 1.01, and then the slope of my secant line is 2.01. Okay, and then say, how about a really, really close number, close to 1, but not at 1? How about 1.001? Then the slope of my secant line is 2.001. Okay, so now look at the pattern. As x gets closer and closer to 1, what happens to the slope of my secant line? It appears that the slope of my secant line is getting closer and closer to 2. Okay, it's not moving off of 2 that appreciably. And what else happens? Well, we show graphically and dynamically that as the abscissa of Q approaches the abscissa of P, the points that make up the secant line start to line up with the points that make the tangent line. So we could be onto something here. We could say that, well, since we're getting close to P, we could almost say that, and these points are lining up. We know from algebra that parallel lines or identical lines have the same slopes. So the secant line is becoming identical to the tangent line, and when that happens, they have to essentially have the same slope. So at least from this perspective, the slope of the tangent line could be pretty darn close to 2. But we still need to do another check, okay? There's still a little bit of a gap here in our reasoning, and we need to check another approach. How if we were to approach P from where if we were to select our Q, that is, select our point Q such that the abscissa of point Q is less than the abscissa of point P. And then we'll drive Q toward P by increasing the values of the abscissa of Q. So we need to do it from the other direction. So that'll be our next endeavor. So let me show you some slides here. So let me paste this into the white smartboard. So Q approaches P from the left this time. So let me go ahead and accentuate the secant line using, say, a red color. Right here. Here's our secant line, and you can see Q is way to the left of P on the parabola. Now remember, both P and Q have to lie on the parabola, and then my targeted tangent line is stuck way out here. Okay. So again, we still have the same formula. We have the slope of the secant line. It's a carryover. MPQ, using the same formula, is equal to the abscissa of Q, which is x squared, not the abscissa, but the ordinate of Q, minus the ordinate of P, divided by the abscissa of Q minus the abscissa of P. Okay? And we're still going to solve the same problem. This time Q is walking along the parabola toward P from the left direction. So, and the way we walk Q toward P is we change the values of x. Don't change the values of y, we change the values of x. Okay? And so divided by x minus 1. So we're going to build another table this time. Let me see if I can copy this table. Nope, I guess not. I'm not going to mess with it. Okay. Insert table. All right, and then let's take our table and let's drag it down here, and let's fill in the table now. Okay. So we'll have x. Now remember, x is less than 1. Okay, and then we'll have MPQ, the slope of the secant line. So MPQ is the slope of the secant line, and we're going to walk x toward the abscissa of P, which is 1. So if we start from the left of point P, say 0. 0 is a good starting point. Then we calculate that the slope of the secant line is 1. So just plug in 0 and you'll see that negative 1 over negative 1 is 1. So that's the slope of the secant line. Now how about we need to advance toward 1. So we'll crank up x to 0.5 and we'll discover that the slope of the ensuing secant line is 1.5. Okay, so for instance that could be this illustration right here. Well, not quite, because Q is still to the left of 0. That could be, say, like Q is right there, for instance. Okay, crank up x again to say 0.9. Okay, that's getting pretty close to 1. And we'll note that the secant line is 1.9. I need to add a couple more rows if I can. Okay, so how about we advance to 0.99. So we're pretty close to 1, but we're not quite at 1. And at x equals 0.99, the slope of the secant line is 1.99. And just for good measure, let's do one more. Say 0.999. Well, the slope of the secant line is 1.999. All right, now look at the pattern as x gets close to 1. What do you observe in the output values of the slope of the secant line? Well, they're getting pretty close to 2. So we have an important conclusion to draw here. No matter which direction we approach P, either from the left or from the right, okay, in this case we approach P from the right, it appears that the slope of the secant line approaches 2 in both cases. Okay? So no matter which angle of attack, from the left, from the right, the secant line slope converges to 2. Not only does the secant line slope converge to 2, but the points, all of the points that make up that secant line, line up with all the points that make that tangent line. So essentially these two geometric objects, the secant line and the tangent line, become the same thing. Okay? And so the takeaway is that the slope of the tangent line now is 2. And now we can answer the question that we asked earlier, which was, find an equation, right here, find an equation of the tangent line to the parabola y equals x squared at P11. And what is m? M is 2, okay, by construction or discovery. M is equal to 2 from the tabular approach. Now notice that we had to create two tables. We had to create a table for the right side and a table for the left side. And we had to show that the limits from both sides of P were the same. Now if the limits happen to be different, then M is not discoverable. M doesn't exist, and there is no equation of a tangent line. So we have to make sure that we use those two tables, from the left and from the right. Okay, so the equation then, the answer, ta-da, is y minus 1 is equal to 2 times x minus 1, using our point slope form. Okay, that's your tangent. That is the equation of your tangent line. Lo and behold, you only needed to know the coordinate of one point, and you can use the point slope. There's your tangent. That's the answer. And that's how you find it. Okay? All right, so we can do an example, say a carryover from physics. So let me open up a new slide. And I'll type in the problem from physics. So suppose that a ball is dropped from the upper deck, make that upper observation deck of the CN Tower in Toronto. We can spell Toronto, which is 450 meters above the ground. That's way up there. Now the question is, we wish to find the velocity of the ball after 5 seconds. Okay, so I don't think, you may have done velocity equations in algebra, but I don't think you ever answered this particular question. What is the velocity after 5 seconds? All right, so let's explore how we deal with this. Now, from physics, we have a position function, which is usually denoted by s. So the position of an object with respect to time t, when it's in free fall toward the surface of the Earth, would be 1/2 times the gravitational constant of Earth t squared. So this is derived from physics. Okay. Now, and since we're dealing with the metric system, because our distance offset is in 400 meters, we'll have to use the metric equivalent of the gravitational constant, which is 9.8 meters per second squared. Okay, so that means that if we climb to the top of this tower and we drop the ball, the position with respect to the platform from which we dropped it as a function of time would be 4.9 t squared. All right, so that's our position function. And of course, the final position would be 450 meters from the guy dropping the ball, okay? All right, so now, what is velocity? So velocity, there are two kinds of velocity, okay? We have what's called average velocity, which is something we're most accustomed to. So let's define a parameter called average velocity. So average velocity is equal to the position, say at some time t2 minus the position at some time t1 divided by the change in time. Where t2 is greater than t1. Okay, so t2 is greater than t1. So, from algebra, you may have heard that rate times time is equal to distance. Okay, well, average velocity is basically your rate, which is equal to your distance, which is the difference in the positions on the number line, for instance, divided by time. So this would be the analogy. Okay, so, and what is average velocity? Well, here's one perspective we can take. Let me pull up another graph for you. So let's consider this graph. Now, here is our position function, and the origin in this case would be, say, the position from which you drop the ball from the tower. So this would be our platform right here at 0. And the ball makes a parabolic trajectory. Okay. Now, the slope, look at the note here. The average velocity would be the slope of the secant line. And why is that? Because here is our T2, and then here is our T1. Okay, and then S, here's S. So S at T2 is denoted by point Q, so let me annotate that. So this is S of T2, and then here is our S of T1. Okay, now we take the slope of this secant line, and then right here, and that would be our average velocity. Okay, so now, so obviously what we're interested in pursuing would be the slope of the tangent line. Okay, that would be our instantaneous velocity. So in this case, so say a plus h. So for this particular problem, a would be 5 seconds. We want to know the velocity at 5 seconds. And a plus h is 5 plus h seconds where h is greater than 0. Okay, so that's how we're going to solve this problem. H is greater than 0. So in solving for the instantaneous velocity, which will be the velocity at 5 seconds, which is the answer to our question, we need to drive h towards 0. In other words, we need to take this point Q and we need to make it get very close to P. So, and the only way we can get Q to get very close to P is if we take H and we make H smaller and smaller and smaller. You see what happens if we make H smaller and smaller? As H goes to 0, this little point right here on the t-axis lines up with this point T1. And when we do that, by our constructions from the previous examples, the secant line will line up with the slope of the tangent line. And so how do we deal with that? Well, we use the tabular approach. So a couple of formulas for you. We can say that the coordinates of P would be the abscissa of P is A, and the ordinate of P is 4.9 A squared. I just take A and I substitute it into the formula for, I took A and I just substituted it in here, so S of A, okay? All right, because S is our output. And then the coordinates of point Q, well, point Q's abscissa is the abscissa is A plus H, and then we just take A plus H and we substitute it into our position function, and that would be 4.9 times A plus H squared. Okay, so there's our point P and Q. And then the slope of the secant line well, that's just, that's what, Q, the ordinate of Q minus the ordinate of P divided by the abscissa of Q minus the abscissa of P, right? And so let's go ahead and plug in the quantities. So the ordinate of Q is 4.9 times A plus H, quantity squared, minus the ordinate of P, which is 4.9 A squared, divided by the abscissa of Q, which is A plus H, minus the abscissa of P, which is A. Okay? And so we translate this, or we recast the problem now into a limiting problem. So the slope of the tangent line, which is our velocity, okay, or actually, technically speaking, it's called our instantaneous velocity. Yeah, in Webber sign, they'll call it the instantaneous, which is the slope of the tangent line, which we use the letter M for, okay? So M is equal to the instantaneous velocity. And we can formulate it in terms of a limit problem. This would equal to the limit as H approaches 0 of MPQ, just like as we did before. Okay, and so that's the limit as H approaches 0 of 4.9 times A plus H squared minus 4.9 A squared divided by H when I simplify the denominator. And of course, remember, H cannot be 0, because if H were 0, you'd be dividing by 0, and you can't do that. All right, so, okay, so, and also we said that A is 5, right? So note, A is equal to 5. So that just leaves one unknown, one variable, h. Okay, so now that means it's table time. So let's insert a table and fill in the table. And I think there's one already worked out for us. So let's understand the table. Oh, I can do it again. Let's see. So let's study this table here. All right. So in this table, we have A is equal to 5. So this is A right here. I'm circling A. A is always 5. And we're approaching A, which is equal to 5, which is the abscissa P. We're approaching P from values of A bigger than A. All right. So in this case, look at this number 6. So this means that H is equal to 1. Right? And so this sixth value is, say, the abscissa of Q. In this case, H is equal to 0.1. In this case, H is equal to 0.5. Excuse me. And here we have H is equal to 0.01, and H is equal to 0.001. So you see how we're fulfilling our requirement that H approach 0 right here. The pattern of H's is approaching 0, and at each step of the way, we recalculate the slope of the secant line. So these are slopes of secant lines. Right? And look at the pattern of numbers. Can you surmise what the slope of the tangent line would be, which would be your instantaneous velocity? Well, judging by the pattern, it looks like it's going to settle around 49 meters per second. So we could say d at 5, which is equal to the instantaneous velocity, is equal to 49 meters per second by tabular construction. Okay, so that's what we have. Now, the question is, now note I emphasized in the previous example that we had to select Q, we had to pick tangent lines that were on either side of P. Technically speaking, we should do that. We should choose our Q, say, we should build another table where our Q's are, say, the abscissas of Q are less than the abscissas of P. So I'll leave it to you as an exercise to say, how about A is equal to 4? Okay, so, no, I'm sorry, A is still held at 5, but in this case, we'll reorient the table to go, say 4.9 is less than T, which is less than 5. Okay, well, maybe not, no, actually we need to start a little bit further away. Say 4, okay. So we should do that to confirm that we'll converge to 49. Say 4 is less than T, is less than or equal to 5. Okay, yeah. And then say 4.1 is less than T, which is less than or equal to 5. So in this case, we're driving our abscissa of Q toward 5, toward the abscissa of P. say, okay, and so just do a number of examples like this. So solve the same problem, and you should get the same result of 49 meters per second. So in this case, A is 5, and then you'll get the ensuing values of the slope of the secant line. So in this case, the secant line MPQ, say, would be the ordinate of Q, which is, say, 5. I'm sorry, not that would be not 5, but 4.9 times 4 squared minus the ordinate of P, which is 4.9 times 5 squared, and the numerator is a negative number, right? But so will the denominator, so everything will stay physically correct. Okay, so there's the slope of the secant line at where Q, the abscissa of Q is, say, 4. So we could say start right here. That would be 4, and then we'll walk along the parabola up to P. Okay, so you should verify that you'll get 49 meters per second when you go in this direction as well. Okay. All right, so that takes care of section 2.1 of your text, and that will be the end of Lecture 2, Part 1. So let me see if I can save this. Save as. I'll try to save it as a PDF document. It hasn't been working very well recently. File. Export as PDF. Let me see if I can export it. Yeah, it doesn't look like it exports very well. It doesn't export the web pages. So I'm not going to export these. These lecture notes are actually online as well. So what I will do is I'll go ahead and save the video part for your reference. So I'm going to stop talking.